So we're going to go over section 11.6, and what I'd like us to do to kind of start this is play with a few logarithms just to kind of pique your curiosity, and maybe you can see a little pattern here. So let's take the log of 5. So log of 5, and then the log of 50. And let's try a couple more. Log of 500. Can you see a little pattern here? Can anyone predict what the log of 5,000 would be? All right, 3.69. So there's something interesting happening with the log. When you multiply these numbers by 10, the log goes up by exactly 1. So the logarithm has some strange properties to it that we need to understand. Now, today we're going to be kind of working on understanding the properties, and then on Wednesday we're going to apply them. Now, just kind of a heads up, we're spending all Wednesday, all day on one section. What's that tell you? It's challenging, yeah. It's not a day you want to miss, all right? So let's work with logs, try and understand some of their properties, and then we'll use them on Wednesday to solve logarithmic equations and exponential equations as needed. Now, first thing I'm going to start with is a list of some properties, and I'll kind of fill them in as we need them and as we use them. So leave yourself some room because we might fill in some at the bottom. We're going to work on something called the product rule, the quotient rule, and the power rule. So all three of these are going to be properties that we'll spend some time on. We'll start with the product rule, and the product rule kind of is hinted at when you look at some of our work with exponents. Now, how's that? Well, remember with exponents, you can have something like a to the n times a to the m. And what happens when you multiply things with the same base? What do you do with their exponents? Add them. So a product turns into an addition up here. And the same thing goes true with logarithms. So if you have the log base b of m times n, the log of the product becomes the sum of the logs. So kind of a strange property, but that's what we've got. Let's play with that a little bit. And maybe after a couple problems, we'll try and go back and make sense out of how I started this in terms of, gee, how come we got that strange sequence of numbers when we're working with a logarithm? It's log base b of m times n equals the log base b of m plus the log base b of n. So you're turning this product into the sum of two logs. Does that help? Okay. We'll start with problem number 34. Now, probably because I'm recording this, I was careful to put log base b. I'm usually a little bit lazier, but this logarithm property applies to the log of any base. It could be base 10, could be base 6, could be base e. Doesn't matter as long as it's a number different than 1 and greater than 0. Problem 34, they actually don't write a base. So what base is kind of understood to be there? 10. Good. Now, this is the log of a product. I can split that up into the sum of two logs. And that's it. That's what they're looking for. Let's take a step back and look at problem number 32. Problem 32 is going to ask us to go a little bit farther in our work here. Log base 3 of 27 times 5. Well, let's start by separating those using our product rule. what would that be? Good. Log base 3 of 27 plus the log base 3 of 5. This first term is something we can simplify a little bit. What power of 3 gives you 27? 3. So this would be 3 plus log base 3 of 5. Now, as far as the rest of this is concerned, log base 3 of 5, we'll learn how to calculate that a little bit later in this class. But for now, we're just going to leave it like that. Let's go back now and understand what was going on with that sequence of logarithms that we worked with earlier. So, for instance, we had the log of 50. And what I'm going to do is rewrite that as the log of 5 times 10. Now from there, we can break that up into two logarithms using the product rule. So that would be the log of 5 plus the log of 10. But now let's take a careful look at this. What base is understood to be here? 10. Good. What power of 10 gives me 10? 1. So really what I got was a log of 5 plus 1. I'm going to leave it like that. Let's look at the log of 500. And similar to what I did above, I'll break that up as the log of 5 times 100. Can someone do some more work with that? What else can I write next? Log of 5 plus a log of how much? 100. All right. Yeah, and again, it's understood to be base 10. So let's take a more careful look at this one. What's a log base 10 of 100? 2. Yeah. Now, if again, if you're not good at that, there's another way out on this one. You can take the log of 100 right on your calculator. That should give you 2. That only works for base 10. Anyways, log base 10 of 5 plus 2, etc. And you can see that every time you multiply by 10, you're really going to be putting another 0 here and adding 1 more to the logarithm. That's why we got that strange kind of sequence of events. So log of 5,000 ends up being the log of 5 times 1,000. Or let's kind of fast forward. Log of 5 plus the log of 1,000, which is log of 5 plus 3. And so on. So this pattern can keep on going and going and going. But there are other patterns and rules to get familiar with. So let me introduce another one. And it's going to be our quotient rule. We'll get some more practice with all of these, so don't worry about it if you're not quite confident with these yet. The quotient rule, again, draws its motivation from our work with exponents. When you have two things with the same base and you're dividing them, what do you do with the exponents? Subtract. So this would be a to the m minus n. So a division turns into a subtraction. Same thing with quotients. The log base b of m over n. So the log of a quotient becomes the difference of the logs. It's log base b of m minus log base b of n. So that's the second of our 3 rules there, is the quotient rule. Well, let's keep going then. Let's try problem number 40 next. So log, and this time they use ln, but that's okay. This still applies to ln much in the same way as it would to anything else. ln of 9t divided by 4. Oops. Someone want to take a shot at it for the quotient rule? Now, just to help out, if you wanted to, you could write it as log base e of 9t over 4. I don't see any reason for that in this particular problem. The properties of the log work for any base, including e. Did you want to give that one a shot? No. All right. Slightly declining. All right. Good. So this would be the log base e of 9t minus a log of 4. It's the log of the numerator minus the log of the denominator. There is a little bit more we can do here. Does anyone see it? How about this here? 9 times t.
That's going to be anything, right?
Anything. Yeah. Well, that's the product of 9 and t. Hint, hint. Product rule. Yeah. Log of 9 plus a log of t. And we still have the minus log of 4 there. Good job. So we can use a product rule after we use the quotient rule. So nice. Now, typically you're not going to see this written as log base e. What you'll see in the book is ln of 9 plus ln of t minus ln of 4. That's what they're going to use. And that's fine. You know, I'm not going to complain either way you want to write it. Typically, people will use ln.
The way that that's written up there, so it's log e 9t, so that's all like level.
Yeah. So,
It's like an exponent.
well, the e is the base there, so it's kind of a subscript. You're right. So it's not on the same level with that. It's just telling you the base. So you're looking for something that you can, raise to a particular power to get 9t, whatever that happens to be. All right. Let's try another one. Anything else on 40 before I move on to 50? Oh, it was 44? Okay. Thank you. My bad.
So log e and ln are interchangeable.
Yes. Just like the square root and something to the half power. They're interchangeable. In fact, quite often when I'm just calculating something for myself on my calculator, I'll raise something to the half power rather than take the square root. I don't know why. It's just the way I roll on that one. All right, Sandy, you're my official checker now. Make sure this is problem 50. Log base 6 of 1 over 36r. So start by applying the quotient rule to this one. And then we can go a little bit farther on this one. Actually, a reasonable amount farther. But let's see what we can get. Start with the quotient rule. Any takers on the quotient rule? Good.
Base 6, 1.
Log base 6 of 1.
Minus log base 6, 36. Plus log base 6.
Oh, nice. He's going above and beyond too, so he's going to expand that. Good. So the first pass is just the quotient rule, right? Log of the numerator divided by the log of or minus the log of the denominator. But what Josh noticed is this. Log base 6 of 1. What I have here is a product. Now, let's be careful here. If I wrote log base 6 of 36 plus log base 6 of r, I would have made a mistake. And the mistake is kind of subtle. It's very sneaky. So let me help you out with that. Or you can write it, but here's what's going to go on with it. Let's put parentheses around that. which means that when I expand this, I expand it in the parentheses, I still have the parentheses there. But where you have to be careful is that term has, if you were to write it without parentheses, you have to distribute the negative to both logarithmic terms. All right, so if you're going to write it without parentheses, that's fine. But what you should write is log of 6 minus this minus this. They both be minus. Before I finish cleaning this up, let's do one more thing here. What power of 6 gives me 1? 0, right? So the log base 6 of 1 is 0. How about the second one here? What's the log base 6 of 36? 2. So it'll be a 0 minus 2. I guess I should keep the parentheses there so far. Plus, well, there's not much I can do here, log base 6 of r. So the 0 just kind of disappears. You could, if you wanted, to distribute the minus. So I get minus 2 minus log base 6 of r. Or you could leave it here in parentheses with the minus sign out front. That's fine. Either one of these is fine. I don't need to see the 0 though. Bless you. Let's keep going with some of our rules. The last rule that I have to introduce is something called the power rule. Sometimes I'll call this one the parachute rule. Just kind of what it seems like to me. Bless you, squared. All right. So what happens when you have the log of something to a power is that this term here can kind of parachute out in front. It just jumps out in front, and you end up with r times the log base b of m. And that's probably one of the most important properties of logs, because it eventually is going to allow us to solve exponential equations. So let's practice with this a little bit. We'll start with problem number 52. ln of z to the 9th. Well, this is a nice friendly one to start out our power rule with. Does anyone want to take a stab at it? I know it's the first example, but anyone good on that one? Wow, you guys rock. Yeah, the 9 comes out in front, so 9 ln of z. Wait a minute, wait.
That was easy.
That's it. That's all we're looking for on that one. All right.
Is the z little or the 9 an exponent?
No, the 9's an exponent.
Okay.
Yeah, so the 9's an exponent.
What was it, r?
Oh, yeah, the formula back here. So let's try problem number 54 next. The log of the cube root of 7. Got it, Tom? I'll tell you what, let me just kind of leave that there for a second. Oh, you know what? Did I give you the rule for dealing with the log of a root? No? That's because there isn't one. All right. So we have to use the rules we have. But here's the thing. This is something we learned a while ago. We could rewrite cube root of something as cube. Yeah, nice. You guys rock. All right. So this is the log of 7 to the 1/3 power. And having written it like this, now we can use our power rule, aka our parachute rule. So this would be 1/3 the log of 7. And even though it's not written, it's understood to be base 10 there. Let's follow that one up with problem number 58. And I'll help you out with 58. But you help too. So it's the log base 3 of the square root of 10 to the 5th power. All right, so it's a good bet we need to do some work with the radical there. So let's do that first. Square root, what can I replace that with? Yeah, something to the half power. So I've got something to the half power and then something to, or raised to the 5th power. When I get rid of those parentheses, what are those two exponents going to do? Are they going to add, subtract, multiply, or divide? Good, they're going to multiply. So log base 3 of 10 to the 5/2 power. Because those two multiply. In fact, if it makes it easier, you can think of that as 5/1. But the exponents multiply. What's the last step then? Good. 5/2 log base 3 of 10. Now later on, we'll learn how to calculate log base 3 of 10. Right now, the most that I could say is that it's somewhere between 2 and 3, right? Because 2 squared is 9, 3 squared is 27. So it's somewhere probably closer to 2 than 3. One more one for the power rule. It's problem number 56. Log of e to the negative 1st power. It's not written. So what's the understood base here? 10. So it's really log base 10 of e to the negative 1st. And that's unfortunate that it's 10 and not ln. But let's just finish it off. The minus is going to come out in front. So it's minus the log of e. You can put the base 10 in there or not. It's up to you. You don't have to have it. It's understood. If this was a little bit different, if it was ln of e to the negative 1st power, that would simplify a lot. This is the same as log base e of e to the negative 1st power. Can anyone tell me how that one's going to simplify? You had one like this on your test. -1. Thanks, gentlemen. -1. You can perhaps see a little bit easier if you take the -1 out in front, like this, and then ask yourself, well, what power of e gives me e? Oh, well, the 1st power. So it's -1 times 1, which is your -1. But it's nice when you're taking the log, the natural log of something with e there, because they're going to cancel out very easily. We're going to start working with these operations kind of combined. And the goal here today is to try and get you really good with these fundamental skills in working with logarithms, so that on Wednesday when we apply this, you'll be up to speed. You can work with them to help solve exponential and logarithmic equations. Right now it's just kind of learning the skills. So we'll keep going with problems like number 64. So the log of x, thanks, x y squared z cubed. So, okay, this is the log of a product. Now we've seen this before with one term, or with 2 terms, but now with 3. But the idea with 3 terms is the same as it was with 2 terms. The log of a product becomes the sum of the logs. So that turns into the log of x plus the log of y squared plus the log of z cubed. So, am I done there? Is there anything else I can do with that? Yeah, and use the power rule here now. So this is the log of x plus 2 log of y plus 3 times the log of z. And that's it. All right, let's try problem number 70 next. Problem 70 looks like this. ln of the square root of xy. Any suggestions on what to do with that one first? Nice, thank you, Bull. Let's write this as a log of xy to the 1/2. Now you need the parentheses on that x around the x and y, because without it, the 1/2 would just be applying to the y and not the x. Oh, yeah, it should be log base e. Yeah, thanks. All right, the 1/2 comes out in front. Well, there's a couple ways you can work this. Maybe I'll go back and rework it a different way. But it's going to be 1/2 the log of xy. And now here's where you got to be careful. This is where, kind of like our problem earlier, you know, I do. I wish I wouldn't have changed over to log base e. Don't need it in this one. But here's what happens. We're going to expand this, but I got a number out in front here. I got a number out in front, and that number is a 1/2. So let me rewrite it then. But when I expand it, what rule am I going to use to expand this? Product rule, thank you. So it's going to be the log base e of x plus the log base e of y, like that. One of two things has to happen. Either you have to have parentheses around this, or when you distribute it, you have to distribute that 1/2 to both terms. So if you wrote it like this, that would be wrong. That 1/2 needs to distribute itself to that second log term. So let's squeeze in 1/2 out here. You could write it like this or this. Doesn't matter which one. Both of them work. Now, what we're going to move into is using these rules the other direction. So we're going to start out with stuff like this and try and write it with one logarithmic term. By the way, you could have also written, 1/2 ln of x plus 1/2 ln of y. I probably should have just left it there in terms of ln's. There wasn't really any need in this problem to rewrite it. But we're going to start working backwards, which is going to mean moving things up into the exponents, using your quotient rule and your product rule for logs. It's going to start with problem number 76. 2 times the log of x plus 1/2 times the log of y Now, if I wanted to combine these together, I can't quite use a product rule in a backwards direction just yet. I've got to get the coefficients out of here. So I'm going to bring this up here and this up here. What's that going to look like? Well, it's going to be the log of x squared plus a log of y to the 1/2 power. What's nice is I got rid of these coefficients. They're both 1. So now I can use the product rule. What would this look like using the product rule? Good. Now, somebody in my last class noticed that, all right, well, log of y is, or y to the 1/2 is the same thing as the square root of y. If you want to write the square root of y or not, I'm not worried about it in this problems. But, gentlemen, you're exactly right. This is log of x squared times the square root of y, or y to the 1/2, whichever notation you prefer. Let's try problem 78. So minus 2 log of x minus 3 log of y plus the log of z. Now I might be a little bit different than my colleagues in this one, but here's what I would suggest, and it's the fastest, easiest way to do this problem. In addition to taking up 2 into the exponent, I'm also going to get rid of the negatives. Same thing here with the 3. I'm going to take the negative up into the exponent as well. So let's see what that would give me. That would give me the log of x to the negative second plus the log of y to the negative third plus the log of z. What can I do from there? Anything? We will eventually, but not in this step. Let's just bring them all together first. Yeah, be the log of the product. Good. So this would become the log of x to the negative second, y to the negative third times z. Now, Josh, I think you're a little bit concerned about these negative exponents, and that's good. I do want you to get rid of those negative exponents, but it's pretty easy from here. The easy thing from here is because these are negative exponents, I can just move them down to the denominator. So this becomes a log, well, I'll have an x squared y cubed in the denominator. Where does z go? Yeah, it stays on top. It didn't move, so z like that. Nice. So, boy, there's a lot of ways you can do this problem, but this one is the best. So just get rid of the exponents. Take care of any negative exponents when we get down to this point. How are we doing on 78? Looking okay there? Now there's kind of an important thing that I want to emphasize in relation to problem number 78, and that is right down here when we had the sum of 3 logarithmic terms. The sum of the logarithms became the log of a product. And I want you to practice that a little bit more to get good at it. So here's one more practice problem. It's not in the book. The first one to laugh gets a stamp of intellectual nobility. There you go. Ah, there we go. A couple people are still looking at that. All right. Come on, give me some love on that. I waited an entire semester for this one-liner here. Come on, give it up. All right. Log cabin. All right. Yeah, I know. Keep my day job, right? Okay. The same idea is happening here. That you're just turning the sum of logs into the log of a product.
Whenever we do that, it's always good to always keep the parentheses right there.
I did here because it brings it together nicely. Yeah, it's not a bad idea. One thing that I do want to emphasize is that you have to have the log of something. You can't have, just log by itself any more than you could have, for instance, square root. You need to have something under the square root. If somebody just wrote a square root, you're like, square root of what? Same thing with logs. It has to be the log of something. So there always needs to be something next to that log. And it can be almost anything. All right. Let's keep going. one of the promises I made to you a little while ago was that we'd be able to calculate the log of any base. And to do that, you need something called the change of base formula. So let's see that. Change of base formula. This is for when you're stuck calculating log of something to, a horrendous base that you're just not all that good with or familiar with. For instance, let's try the log base 6 of, I think this one works, 7,796. We'll find out if I got that right in a minute. But, most of us can't look at that and go, oh yeah, 6 to this power gives me that number. And that's okay. Whenever you have log base b of some number, we'll call it a, you can use this formula. Take the log of the number and divide it by the log of the base. Now, what logarithm am I using for that change of base formula calculation? What's understood to be there? 10. There's other ways to write this, but it's understood to be base 10 in both the numerator and denominator. So how would that look here? What would that look like if I was going to apply that here? Well, good. It's going to be log of the number, 7776, divided by the log of the base. The only place that you can make kind of a mistake or screw up is while you're using your calculator, you got to make sure that you use parentheses around the log. So let's kind of zoom in a little bit. So it's going to be log of 7776 divided by log of 6. And did we get something even? Yes. Got a 5. So, nice. So log base 6 of 7,776 is 5. Did you use a right So the biggest mistake that I see people making when they put this in is they don't put a right parenthesis around that first number. So if I left that out, here's what's happening. It's going to take 7,776 divided by the log of 6 and then take the log of that. So this should give you something much, much different. Yeah, 3.99 something. So, like I said, much different than what we intended. So let's try one out of the book. It's problem number 96. If we get this right, we can be done. So log base 7 of 3. Try and calculate that. And then I'm going to show you how to check it, how to prove you got this thing right. And it's a test question that I ask often is prove your answer is right. But right now, just try and calculate the log base 7 of 3. Now, I'll give you a hint, and I'm just thinking out loud. 7 to the first power is 7. So whatever I get for the number here, it's going to be less than 1. All right, so that's the only observation I'll make. What number are you guys coming up with? Same one here? All right. So about 0.5646, rounded off to the nearest 10,000th. You still running into problems with that one? Let me write a little dot here. This little dot means is approximately equal to or about 0.5646. I'll come back in a second and try and see what's going on there. Let's see if we can't check this. Now, how are we going to check this? Now, sometimes I'll say, check it, prove your answer is right on the test. And what people will do is they'll calculate it the second time. That's not what I want. I want you to, go ahead. You
7
exact,
to the 0.5646 power.
perfect. This to this power should give me this. I can rewrite it using exponents. Now, what's even cooler is that you can check it without really breaking a sweat here on your calculator. I want 7 raised to this power. Now guess what? Your calculator has that stored. So you don't have to type that in. If you hit the raised key, I want to raise it to my previous answer. Well, my previous answer is right down here. What do I have to do to get that button, get to the answer button? Second, and then the opposite key, etc. So it's going to give you 7 to that power, and when I press the enter key, let me zoom out, I should get, what? 3. Yay. Nailed it. Absolutely perfect. Now, if you're feeling lazy, you can do 7 raised to the 0.5646 power. Am I going to get exactly 3 if I do this? No, but I should get reasonably close enough to convince myself that I got it right. Okay, so a little bit over 3. Nice. Are you able to follow along with those things? I mean, the one thing that I want you to do is to be able to prove that you got your answers right. I mean, you should want to do this for yourself, I would hope. But sometimes I'll ask it as a test question. And what I'm expecting is 7 to the 0.5646 equals 3. Okay, let me give you some homework. Some of it is stuff that we haven't quite covered yet. And in total, I've really tried to keep the homework set to a minimum. Now, because of that, it actually sounds like a lot because I'm going to be listing a lot of problems. But they're all broken up. 19 through 25, 33, 39 through 45, 51, 59 through 65, 75 through 79, 97, 103, and 105. So 1, 2, 3, that's another 3 there, 6, that's another 5, 11, 12, 16, 17, about 20 problems out of over 100. It's not bad. I really encourage you to do these things. It's going to be a challenging section Wednesday, so keep up with it. If you have some questions, let me know. See ya.